All right, guys. All right, guys, so we're talking about maximums and minimums. There's two kinds. Hey, guys, up here. Two kinds of max and mins. You have an absolute max or min and a relative max or min. The absolute means the graph will never go higher or lower than that point. So like an example with an absolute, like a parabola, maybe. Do you see how the vertex up here, that's the absolute highest that graph would ever go? Okay, that's an absolute maximum. It could also be a minimum. It's just nothing ever goes lower than that. Relative max and mins, that means it's like the top of a hill or the bottom of a valley, but there are other points on the graph that are higher or lower. So like a graph like that. Do we see how that's like, it's a maximum in that little interval, but it's not the highest ever. Same with this. This is a low point on the graph, but not the lowest ever. Do you guys see it? Okay, so that's what we're looking at with these graphs. And we're going to jump around and skip a few things here and there. Let's do number one together. Okay, when you look at this graph, do you see the arrows at the end? Right, so it's going up forever and ever and ever. So is there an absolute maximum? No. Infinity is not a maximum. It's not a defined point. So we just say none. There is an absolute minimum. Do you guys see it? This guy over here? Okay. We don't write it as an ordered pair. I know that's annoying, but we say what the minimum is and then where it occurs. So how far down does this go? -3 at x equals what? 1, 2, 3. -4. The hardest part is counting, I swear. These lines like blur together. -3 at x equals -4. That says at. Oh. That's AT. Okay. Relative max. Do you see a top of a hill anywhere? Yeah. You can also think of like zooming in on different sections. So like if I focused only on this, let's see if my pen cooperates. That's really small. But do you see how that's a maximum? Okay, if you can block out the rest of the graph. Again, not the highest ever, but it's the maximum in that little section. So that's what we're talking about with relative max and mins. So your relative max is this guy right here. So how high does it go? 2 at x equals what? 1, I think. 1? I'm like, now I'm doubting my counting. Yeah, at x equals 1. Okay, relative mins. An absolute min can be relisted as a relative min. So we actually have 2 relative mins here. So what are the 2 mins? What do we see? Well, one of them we already know, right? -3 at x equals -4. I know the line is not big enough for this. What is the other one? -1 at x equals 3. Squeeze that in there. Okay. All right. Any questions on maxes or mins? Yeah.
There's 2 relative minimums, but there's one of them's not like an absolute minimum. You still list some of them.
Yep, just like here, because we only had. Or you mean if neither of them are?
Or absolute.
Yeah, just list all of them.
Okay.
Yep. And you could technically have more than one absolute if they're at like the same y value. You know, if it's like here and here, then you list both of them in both places. So, okay, increasing and decreasing. We go from the left to the right, just like when you read. So just trace your graph. As I'm tracing the graph, is that increasing or decreasing? Decreasing. So that section is from negative infinity to, what was it, -4? 1, 2, 3, 4, yeah. And just use parentheses on everything for increasing and decreasing. Different textbooks do it different ways, whether you include the turning point or not. We'll just do parentheses. Okay, the next section then, like right here, what do we think? Is that increasing or decreasing? Increasing. So we're increasing from -4 to 1. Yep, we're going to have a union. What's the next section doing? Decreasing. So I'm going to say union. And then what is that? 1, 2, 3. All right. What about that last piece? Increasing. So that would be from 3 to infinity. So you just give me the x values over where it's happening. And every time you had a max or a min, that's where it changes from increasing to decreasing or vice versa. Okay, questions on number 1? All right, do number 2 for me. You guys try. We're going to skip 3. Those of you that like to work ahead, we're not doing 3. Because the closed intervals and endpoint, we're skipping 3.
Would there be 2 relative maximums here?
Just 1. I see 1 relative max and 1 relative min. Just the other end, like, it's just going to keep going up and up and up. There's no, like, top of the hill. No, there's also not an absolute min because that's 2 a relative max and a relative min is all you have.
Okay.
Okay?
Okay.
Changing seats. Try to watch it. I try watching it.
Guys, do we see that there's no absolute max or min on this one? Does that make sense? Okay. Give you another minute to finish up. Yeah.
For the middle of the graph, when it goes down, you have to list 2 decreasing because there's a point here that's separated.
No, because I mean, I could put a point here and a point here, and right? Like, there's literally points all over. So it's just showing the x-intercept, but it doesn't actually do anything. Yeah, you just look at the whole section. You're like, this piece is going down. Yeah. Yep. Just like with these points. They don't really matter. They're just there for decoration. Yeah. Don't let them mess with you. All right, guys, what'd you get for your relative max? Good. 3 at x equals -4. All right, relative min. I think it's 1. For real, the counting, hardest part. Okay, increasing. Would you agree that first section was increasing? Yeah. Okay, so did we have negative infinity to -4? Okay, what was your other increasing interval? 1 to infinity, good. And then we just have one decreasing section in the middle from -4 to 1. How do we do? Good, okay, all right, getting it. Okay, yeah.
I thought the left side of the graph was, decreasing because it's going to.
So, but you read it from left to right, so you trace it. Yeah. It's easy. You can definitely talk yourself into, well, no, that's downhill.
Yeah.
No, yeah. But pretend your little dude that you're putting on your graph is going on a trek. He's starting over here, so he has to go uphill, downhill, uphill. Okay. Put a little person on there if you need to. Yes, so absolute mins can be listed as relative mins as well, but not in reverse. Do you see over here on this first one how -3, does the graph ever go below that? Okay. Yeah, because this side of the graph would go, yes. Does that help? Yeah. Okay. All right, guys. Try number 4 for me. You guys do 4. I think that's the last one we're gonna do on the front here. I think we're getting it. Am I right? Yes. Sure. Increasing and decreasing are always x values. Yep. It's where is the y going up and down? Like, tell me the x values where this is happening. Mm-hmm. Yep. Yes, you have 2 of them. Yeah, you'd say this at x equals blah and blah. Okay.
Do we do the same calculus?
Hold on. Hold on.
Multivariable linear algebra?
Yeah.
No.
No. Okay.
I'm actually gonna stop doing it. You know what
I think we can do that.
I know. That's what there are. And she.
Yes. Yeah, good. All right, guys, let's go through this one. Is there an absolute max? No. What about absolute mins? Yes, and I'm just going to write it 0 at x equals plus or minus 4. Okay? What you wrote, totally fine. Like, you can write it as two separate ones, too. I'm just, writing less. Do we have a relative max? Yeah, it looks like it's supposed to be at 4. I don't know if the dot actually made it there. So 4 at x equals 0. Good. Now, what about our relative mins? Yep, same as we did for absolute. Okay, where are we increasing? Yep, -4 to 0, and good. Where are we decreasing? Excellent. Okay. How we doing, guys? We feel pretty good on that? Okay. All right, we're going to do some of this next question. I know it's not as scary as it looks, okay?
Yeah. Well, it's like a multi-part exercise. What if you
Okay. All right, guys, so this graph is just kind of different looking than the graphs you have. It's just a much larger scale. It's just a piecewise graph, a lot of sections. We're answering the same types of questions. Where is this increasing and decreasing? I only see one section that is increasing, 0 to 2. All right, decreasing, I believe there are 2 sections that are decreasing. 2 to 4 and 6 to 8. Anybody know what it's called in this little section from 4 to 6? Constant, yes. It's not increasing or decreasing, it is constant. Okay. All right, local mins and maxes. Let's just talk about this together. These points sort of on the corner of the constants, those are not maxes or mins, okay? Because it's not technically lower or higher than the points right next to it. You go on either side, right? It's just sort of a weird turning point. So we get nothing out of these, okay? That leaves us with the end point on each end and this point up here as our choices for maxes and mins. So I actually see 2 local or relative minimums. What are the 2? Local means the same as relative. So what do you think, guys? What are the minimums? Perfect. 0 at x equals 8 and 1,000 at x equals 0. Does that make sense? These endpoints can be relative or local mins or maxes. And then it looks like we have one local max or relative max. It's also the absolute max. Where is that? There we go. Okay. So the graph just looks a little different, but you're answering the same type of questions. We are not going to do average rate of change. It's just slope, but we're not going to do it. Try number 4 for me. See if you can find those values. I'll give you guys a second to try. You're using the graph to find these. So R of 0, R of 3, and what is T when R of T is 100? All right, guys, what'd you get for R of 0? 1,000. You see it? Okay. What about R of 3? 100. You guys are awesome. Okay, did we figure out the last one? Yeah, 7.5. Anybody going, what in the world? Where did 7.5 come from? Okay, so it says find T when R of T equals 100. So I'm just going to draw a line here at 100. There's 100, right? That's the point we're talking about. What is the X value that goes with that? Do we see how this is 7, so that's 7.5? Okay, you're just kind of working in reverse. Instead of being given the X value, you're finding the X value. Okay. All right. Any other questions on this page? Okay. All of them. Actually, we are going to do most of these, but you get to just look at the graph most of the time. All right, let's talk about the different types of discontinuity. The first one is an asymptote. It's also called infinite. I think you're familiar with asymptotes. This is a discontinuity. If you have a rational equation, where is the vertical asymptote in this one going to be, guys? It comes from the denominator, so it's at x equals 2. Yep. So infinite discontinuities or asymptotes are when the denominator equals 0. And the way you would answer one like part A here, I'd ask you the type and location of the discontinuity. You would say infinite. If you say asymptote, I'm going to give you credit. Okay. If you're like, I can't remember that word. And then you say at x equals wherever it is. So in this case, at x equals 2. So for letter B, we'd say infinite at what? At x equals 4, yeah.
you provide it, or if you just draw it, it'd be simple.
Right, infinite. All right, so that's the first type, asymptotes or infinite. The second type is called removable. It's a whole. So this first one, if we go through this, what does that numerator factor into? Good. X plus 3, x minus 3, over x plus 3. What happens with the x plus 3's? Yeah, that's what creates a whole, is when you cancel out a factor. And we did this when we graphed rationals. You don't have to find the y part of the whole. You can just tell me whole or removable at x equals, what do you think it is this time? -3. Yes, it's what would make the factor you canceled out equal 0. So at x equals -3. All right, so letter B, if I just give you the graph, again, this is a whole at x equals what? Did I hear 1? I don't know, but yeah, okay. It's nice when you're just given the picture. You don't have to do any algebra for it. Does that make sense on wholes? And again, you can call it removable, you can call it whole. I'm taking either one of these, okay? Just be aware of the terminology in case a question says, like, where is the removable discontinuity? You know what that means, okay? If you have to write it, I don't care which one you write. The third type is a jump. And this always comes from a piecewise function. So let's do the graph one first. If I give you this graph, do you see how you'd have to lift up your pencil and like jump yourself up to it, right? Okay, there's a big gap there. So this is a jump at x equals 2. Yeah. If I only give you the piecewise equation, you just need to check with this x value. Plug in -1 and see do they match or not. If they match, the two pieces of your piecewise run into each other and there's no discontinuity. If they don't match, then you have a jump. Okay, so if I plug in -1, 2 times -1 plus 1, what do I get? -1, yep. I plug in -1 to the bottom, what do I get? Oh, I wrote the answer. Well, sorry. -5. Okay, do they match? No, do not match. That means you have a jump discontinuity at x equals -1. Questions on the 3 types? Yes, Katie, we're good. You can just write continuous. Because what it would look like graphically, it'd be like, oh, we have our first one. You guys saw this a lot on your Delta Math, and then it was like the other one filled it in. You see how it's like a connected graph then? There's no discontinuity. So you can just say continuous. Okay, let's try a few of those. Do 1 and 2 for me. Let's start with just those 2. You guys try 1 and 2.
something.
Yeah.
So I did negative for this. And then I plugged that into these. And then
Oh, what X value should we be plugging in?
are we doing something what's it called? I thought we were just doing whatever we got the answer we got from this one.
No, you plug in the X value.
Oh, really?
And then just see.
We're not like doing like something greater than
No,
just plugging at 0.
The point we're checking at is 0. Like that's where the jump would. Yeah. Yep. So it's easier than what
I understand it.
Yeah.
All right, guys. What do we think for number 1? Yes. And then at x equals 7. Okay, number 2, what x value am I plugging in to check here? 0. So I get -1 out of the top, and I get -1 out of the bottom one. So what does that mean? Continuous. You guys are on fire today. Are we like ending the unit with the easiest stuff here? Okay, try 3 and 4. And actually skip 4. I'm not going to ask you one this complicated because there's a lot of things going on in 4. So let's just do 3. Okay. Yeah. So you check for a jump at the x value of 2 and -2. And then you also have to look and see, does that asymptote fall in this one? So there's just a lot.
Oh, that's okay.
Nope. I gotta factor the numerator to figure that out, though. Okay, which one canceled?
The whole that positive one and the no, it's not. Oh, in the same place.
Discontinuities, yes. I have to think to like enunciate that word. All right, guys, if we factor, we get x plus 2, x plus 1 over x minus 1, x plus 1. You have 2 different discontinuities. Where is the whole or removable? No. -1. What got canceled out? Okay, and then what makes that factor 0 is where the discontinuity is. So at x equals -1. Then the other one is infinite. At what? Yes, at x equals +1. This other factor in the numerator here, this x plus 2, it does nothing. We don't care about it. We're shunning it, okay? All right, questions on discontinuities? It's trickier when there's more than one in the problem. Okay. All right. End behavior. We've done this before. You've done it in Algebra 2. We're just going to review. reminders on what end behavior looks like, and then we're going to use what's called limit notation. It is very similar to how you wrote it before, but you're going to actually have a limit in what you write. So first, let's review end behavior. So if the degree of the polynomial is odd and the leading coefficient is positive, are we okay with the graph looks like this? Something like that. We're familiar with that? We're not going to fill in the right and left end behavior here, but like the right end is going up, the left end is going down. Yes? Okay. What if it's odd and there's a negative leading coefficient? What does that do? Yeah, so we're going that way then. Okay? Remember this? Like, teacher like dance with our motions. Anything touchdown? I don't know. All right, even and positive leading coefficient. That's just an upward facing parabola. Both ends go the same direction. They're both going up when it's positive. What about when that leading coefficient is negative and it's even down? Okay. All right. So this you know, right? We are familiar with this stuff. Okay. So let's look. Oh, you don't have this? Where did it go? That's so weird. Okay, you just stop at the even and odd. All right, jot down. Let's not do all of them. Let's do 1 and 3. Copy those two down for me. Squeeze them in somewhere on a margin. Okay, let's do number 1 together. So when you have this whole big polynomial, we only care about one term. We care about the highest degreed exponent. So what is the highest exponent anywhere in this? 5. Okay, so this is the only thing I'm looking at. You can ignore everything else. All right, that is odd, and it is positive. So you should be visualizing this shape. All right, everybody with me? Okay, end behavior with limit notation. Let me write the first one. I'll let you copy it down, and then we'll talk about what the things mean. The limit, Lim, of f of x, and then below that, as x approaches infinity, equals, that's asking, as x goes to the right, where's my graph going? Up. Yes, so we would say equals infinity. Questions about the writing of it? Lim, Lim, so that's limit of f of x, underneath that as x goes to infinity, and then whatever it equals, whatever direction it's going. Okay, we have to do the left end also. So limit. Yeah, you don't have these on your paper. Just jot down 1 and 3. I don't know where they went, why they aren't on your paper, but here we are. So as you're going to the left end, you say as x approaches negative infinity. And where is my graph going on the left side? There we go. You guys are used to writing it like this, as x goes to infinity, y goes to something, right? Like that's what you did in Algebra 2. We're just throwing on this little notation, okay? We're just putting that on top of what you are used to doing. So let's go back. So you guys try number 3 for me. Think about which term we care about in that, and then try to write the 2 limit notations. I'll give you a minute, and then I'll write them up here so you can compare. No. It depends on, we picked, this one turned out that way because this is the graph we're visualizing. So as x goes to the right, this is going up. But if it had been, like, let's say this was the graph. No. So you do this first, and you fix, so let's pretend this is the graph we're looking at. You see it? Okay. All right, guys, look at 3. X to the 4th is the term I care about. So I'm visualizing a graph where both ends go up. Oh, did you guys do 5x to the 3rd? It's not written in the right order. So look, I'll give you a minute to redo. Find the highest exponent. I know that's mean when it's not in the right order. Find the highest exponent, drag it. If you saw it, good job. So you're going to be thinking about x approaching infinity and negative infinity every time. And then you look at the graph and think about, yes. Yep. So like, let's say, we aren't doing number 4, but let's say this. You'd be like, okay, it's odd and negative. Yeah, okay. All right, guys, number 3 then. When we fix it, x to the 4th, did you get both of them equal infinity? Okay, because both ends are going up. Okay. You like this? Okay, good. Yeah. All right. Heavy on 9.5 on the test, guys. Okay. All right. We are going to do a way ground. I got to find one quick, and I got to stop our recording. So.